In this lesson, we will now explore the production of green hydrogen from electrolysis. Here, we don't need a conventional feedstock like natural gas or coal, but only electricity and water to generate hydrogen. Now, why is this of interest? As you already heard, hydrogen is already being used at scale, with an annual production of roughly 90 megatons. This uses 2% of the global annual energy supply today, and results in 830 megatons of CO2 emissions, which is more than Germany or the global shipping industry emit. So we want and need sustainable production methods for hydrogen. This is where electrolysis comes into the picture. The electrolysis of water enables the direct electrochemical conversion of electricity into hydrogen. This omits any kind of carbon-based energy carrier, so this process can be entirely carbon neutral. But it has more advantages. An important one being that it enables us to store excess energy from renewable energy sources like wind and solar, and thereby we can decouple energy production and consumption. You will hear about the versatility of hydrogen in the other lessons of this course. What we want to look into in more details in this lesson is the electrolysis itself. In water electrolysis, water, H2O, is split into hydrogen and oxygen using electricity. To understand this process also helps us to understand the origin of the word electrolysis better. The word electrolysis is derived from the Greek words electro, so electricity, and lysis, so dissolution. In other words, the decomposition by means of electricity. Here, you see this process in an acidic environment. In practice, we feed water to the electrolysis cell's anode, where it is split into oxygen, protons, and electrons. Oxygen can be collected as an anode product, while protons are traveling through the ion-conducting electrolyte. Electrons are traveling through an external circuit. More on that later. On the cathode, protons and electrons then recombine into hydrogen. In total, this gives the decomposition of 2 molecules of water into 2 molecules of hydrogen and 1 molecule of oxygen. As each electrochemical reaction has a potential at which it occurs, we can also define potentials and a total voltage for water electrolysis. However, we must note that water electrolysis does not happen spontaneously. In other words, we need to force the reaction to happen. And the more current we force, the higher the voltage and the higher the energy consumption of the electrolysis cell altogether. You can see this in the simplified graph, where the cell voltage increases with increasing current. This is the opposite of a galvanic cell, such as a fuel cell, in which the voltage drops when we, in that case, use more current. In reality, it is more complex, but this simplification already helps us to understand the correlation between current and voltage in water electrolysis. It is worth noting that other electrochemical processes like electroplating or the electrochemical metal reduction follow the same principles. Now, I already mentioned that the cell depicted before was representing an acidic environment. So I hope you already ask yourself, what other environments are there for water electrolysis? As a matter of fact, there are multiple different technologies. So here we will focus on the 3 most prominent ones. This is for one, the alkaline electrolysis, which is historically the most explored type. The acidic polymer electrolyte membrane water electrolysis, which is gaining increasing attention. And the high temperature electrolysis, which promises a high degree of versatility, as it can cope with feeds other than water as well. As you can see, these technologies are characterized by different charge carriers, materials, and operating temperatures. Let's explore their unique advantages and challenges in more detail. Let's start with polymer electrolyte membrane, or PEM, electrolysis. Here, you should already be familiar with the reaction equations depicted on the right. Since this technology is based on a solid polymer as the ion-conducting electrolyte, it is capable of coping with higher pressures, which is a big advantage of this type. The solid electrolyte also allows a simpler and compact layout and results in high gas purities. PEM water electrolyzers can also be operated more dynamically, which is important if you want to use electrolysis to convert excess energy from fluctuating renewable sources into storable hydrogen. However, the materials that withstand the environment of this type of electrolysis cell are very limited and those that are suitable are typically pricey. They also contain perfluorinated polymers, which have come under scrutiny as so-called forever chemicals, and are being banned to an increasing extent. So cost, environmental aspects, and material scarcity are issues. This is very different in the alkaline environment. As you see on the right, though the total reaction equations remain the same, we still decompose water through electricity. The respective anode and cathode reactions change dramatically. The charge carrier here is the OH- ion, so a big and bulky anion is now the moving ion instead of the small proton before. Also, water is now being split on the cathode instead of the anode. Now, this type of electrolyzer has already been proven to work in reality with lifetimes well beyond 10 years. And in comparison to, for example, steam methane reforming, the produced hydrogen is of high purity. The alkaline environment also allows for the use of cheaper electrocatalysts, such as nickel instead of iridium and platinum, that are being used in PEM water electrolyzers. However, this technology is also costly in comparison to fossil fuel-based hydrogen production processes, and the use of a liquid electrolyte makes this technology more complex than other electrolyzers. Also, to couple alkaline electrolysis with renewable energy sources is more complex than for PEM electrolysis. And then there's the solid oxide electrolysis, which works at much higher temperatures. As stated, the operating temperatures are between 700 and 1000 degrees C, whereas the other two technologies were operating below the boiling point of water, which is of course at 100 degrees C. Again, the total reaction equation for solid oxide electrolysis is the same as for the others. But here, the charge carrier is the O2- ion, which is conducted through a ceramic electrolyte. The water splitting reaction, now in the form of steam, happens at the cathode. The materials that are being used in this technology are, despite the high temperatures, fairly cheap and, if operated right, stable over a long time. Also, due to the high temperature, not only water can be split, and the efficiency is high. But the high temperatures are also a limitation. Pressurization is hardly possible, thermal stress is an issue, and so is dynamic operation. So in essence, we can conclude that none of the discussed technologies has a clear advantage over the others. Depending on the application, one or the other may be the most sensible choice. What stands undisputed, though, is the fact that water electrolysis as a whole is an important process to produce green hydrogen. Not just with respect to the growing interest in hydrogen as energy carrier, but already today for its widespread use as a chemical compound.